Good afternoon, everyone. One request from my side. Next time when you log in, please log in using SJ's email ID, because every time we have to admit those who are not from SJ's email ID. Okay, fine. We'll go to our lab session. Okay, can everyone see the slide?
Yes, sir.
Okay, welcome to the lab. In this semester, along with the DSP lab, you are having one more lab named Verilog HDL. Already you have seen the recorded video of Verilog theory in the Canvas classroom. This is the continuation of the theory classes. So we will see what are the who are the faculties involved in this one. Myself and Deepthi ma'am, Nandini ma'am and Rupal ma'am will be the faculties, and as a lab instructor, Ms. Divya ma'am will be the lab instructor for you. So as a part of the syllabus, if you look into the syllabus point, it is same as that of what you have done in the digital design lab. So in the digital design lab, you have done the AND gate, OR gate, NAND, and adder, encoder, decoder. So you have the same thing here as a first part in part A. Along with that, we'll go to the next level, that is creating a simple ALU. That's a 32-bit ALU, but it is a very simple structure we'll do. Then in the part B, we'll be doing with the interface. So what we have done in the digital electronics is just testing the IC, whether it is working properly or not. That much we have done, but we have not, I believe we have not interfaced with the stepper motors, DC motors. Okay, so in this lab, we will go to the next level, take the digital design, what we have done already in the third semester. Along with that, we will do the interfacing with the 7-segment, DC motor, stepper motor, LED and LCD. Then we will do with the digital to analog conversion, that is a simple sine waveform. This by default helps you to do a simple projects, or you can start doing a project using digital designs. So that's what the syllabus is covered for us. These are the outcomes for us. So the first outcome will you will be introduced to write a Verilog code for a combinational circuit in a different level, different flows. So there are 3 flows available by default. It is a data flow, structural, and behavioral. So in the first few weeks, we will concentrate on the structural flow. And the second outcome will be you will be able to design a 32-bit ALU with the adder as well as the logic operations. And the third one is about the flip-flops and counters. So these are the key components which is required to build a processor. So what are the first 3 outcomes are the basic components which is required to build a simple microprocessor or microcontroller. Next 3 is to how to change the clock. If I have a 100 megahertz clock, but some circuit requires only 10 megahertz clock, how I can divide that? That's the 4th outcome. And the 5th outcome, it talks about how was writing a code in a English language, that is in a coding point of view, can be converted into synthesizable format, that is equivalent to the circuits. That anyway we'll explain a little bit more on the course outcome 5 in the theory classes. And the 6th outcome is all about interfacing, where practical exposure will be given for the DC motor and stepper motors and its equivalents. So I hope everyone is clear what you expect from this lab. When you come to the offline mode also, you'll be dealing with the FPGA kit, which is available in our campus, and you'll be interfacing with that also. Okay, what are the prerequisites for this lab? So digital design, which you already learned in your third semester, and the lab. If you know C language, it is well and good. If you don't know, no need to worry, because you can learn it easily. It is similar like to the normal languages, or now how we are talking as a language as a English, the same thing they have taken and they converted into a digital domain. So I hope up to this one, are you clear with the overall idea? Hello?
Yes, sir.
Yes, sir.
Yeah, thank you. Okay, now we'll just go to the basics of why I require a HDL, that is hardware description language. As you all know, that there's a C language you have learned in your first semester as well as in the PU colleges, right? The purpose of C language is to simulate the idea what we have. You'll be writing some, you have some logic, let's say I have to add anything. So in the language, in the C language, what you'll do, you say C is equal to A plus B. But it will never convert into AND gate or OR gate. That will not happen in C language. Whereas in the hardware description language, it focuses on that. When I say plus, it asks for what kind of adders I have to use. Whereas from the top level design, I just say a plus symbol, that's all. Whereas in the digital design, if I want to design adder, we all know for a 1-bit adder, the sum expression is given as A XOR B XOR Cin. So the plus sign should be converted into to the digital circuit. If I want to do that, then I require a hardware description language. Okay, that's the first thing. And as I told already, it gives us a simple words and symbols. Just a symbol is plus sign is sufficient to create adder. If I want a 10-bit or 20-bit, I can still say A plus B. Then it is equivalent convert into 20-bit adder and 20-bit multiplier. It is easy for us. Then from a simple circuit, I can go for a complex circuit like a DSP processor, a microprocessor, or a microcontroller. Now everyone is aware of Arduino boards. Everyone has used the Arduino board. Is that right? That entire Arduino IC chip can be designed using HDL language. We have to just write the logic properly. If the logic works, then we can go for the fabrication. And one more thing, the major thing is the hardware components are concurrent. That you have seen in the digital design lab. That means when I use an AND gate, both A and B are inputs are happening simultaneously. It is not that first A will be there, then it goes for a B. It is not a sequential manner. So I need a language which can see all the inputs as a concurrent. For this point of view, we are differing from the traditional language like C, Pascal, or Photon, C++. We are changing from that to the hardware description language. And along with this, timing is an integral part of this hardware language because that is very crucial for us. When we take the CRO or the DSO, we will see with respect to the timing. So that timing plays a vital role in design. So these are the reasons why we require a HDL lab. Okay, now I have a HDL lab where I will use this language, where I will implement it. So to implement it, we'll go for a device called field programmable gate array. I think someone is speaking. Anusha, can you mute? Thank you. Okay. So similar like why this concept came is, see, for example, in the lab, when we design a circuit, I have an AND gate. Suppose I have given a faulty voltage level. Now what happens there? You might have seen that sometimes your IC will not work. You might have given a complaint that the particular encoder is not working for us, and the decoder is not working for us. Is that right? So if I fabricate and test, if I found this is a faulty one, then I am going to waste lots of money. To avoid that only our HDL language came. Then to support the HDL language, we have a FPGA, which is a general purpose test kit, like a test kit, where inbuilt it has a multiple logic blocks. I think in the digital design, you have a chapter called FPGA and you have learned it, right? So FPGA is inside that it has only logical gates, that is AND or NOT. Along with that, it has a memory, that is a flip-flops, and some 1K of RAM will be available for us. So whatever the code we are writing, it will convert into equivalent lookup tables and it will be dumped in the FPGA. That is easy for us to test our logic first. If the testing is done properly as implementation stage, then we can straight away go for the fabricating an IC. This is the reason why we need to use the FPGA. Then Verilog. Okay, is there a only hardware language available? The answer is no. There are multiple hardware languages are available, but to the syllabus, we are going to learn only the Verilog language. It's one of the hardware description language, and it is easy to describe the digital system. It also has a similar syntax to C. Okay, but because the creator has almost taken from the same syntax and they have used it, the advantage is it is able to synthesize the code and it can convert into logic circuits also. If I say AND, it will create an AND gate for us. Physical AND gate can be done for us. Then it is a case sensitive, similar to the C language. It is a case sensitive. Keep in mind, it is a case sensitive. So there is a difference between a small c and a capital C. Okay. Here is a key component. We have tools. Since we are in the online mode, the online tool what we are going to do is from the joodle.com. It is very easy for us. Just click the link and you can open the link in your canvas also. Okay. I will show you later how the things will be there. Or 1 second. Yeah, this is how the link will be there. Can everyone see the link now?
Yes, sir.
Yeah.
Yes,
So
sir.
the first one is the editor for us. So which I am highlighting for you. This is the editor where we have to type the code. And when you count down, there is a version available. So right now you don't change anything here. Let it be 10.3. Just press the execute button. You can see the result will be here. All your results will be available here. So this tool will not give you a waveform. It will be like your observation book, what you did in the digital design, where you have a table, inputs and outputs, and you will be noting down the values. So it will be like a table for us. Is that clear? What you'll be doing in the online? Okay, so again I'll repeat. You have a IDE which has a space to type the code for us, and there's an execute button. It will execute for us, and if there's a display, the result will be displayed at the black box available there. If there is any error is there, that also will be displayed in the same box. Okay. Okay. Now when you come to the lab, we have the commercial version of Xilinx Vivado, which is for the Xilinx FPGA kit of 2018 version. We initially thought of giving the same to you, but if you want to use this kit, it requires 7 GB to download. If you people are ready, then it is good for us to download 7 GB file and use it so that everyone can use the same Xilinx platform, or we can switch to online mode. So I want a response from your side, which mode you want to have.
I think online is better, sir.
Sir, online is only better, sir.
Okay, fine. Okay, then there's the same link is given in Canvas also. You can use the link. Okay, what are the steps involved in the lab? The general process, what we are discussing, what we'll be doing in the lab in online as well as in the offline will be, first you are going to write a code. That's a Verilog. Then you have to simulate the code. Up to this, online and offline is same. Okay, step 1 and step 2, process 1, process 2 is same. And the synthesis and implementation, you have to use Xilinx tool. So once you come to the college, at that time we'll go for the process 3 and process 4. Till that we are going to hold with the process 1 and 2 only. And few of the assumptions that we are going to make. Whatever you learned in the digital circuits, okay, we know that is a logic 1 is equivalent to the VDD. So when you say VDD, there is always a conflict. So what is the value for VDD? Okay. So in a Verilog, we'll assume it is a plain VDD, and we are not considering on what is the value there. It can be 5 volt, it can be 2 volt, it can be 1.2 volt or 1 volt. It depends upon which IC we are going to define and what FPGA we are going to use. That later stage will take care of that one. And for the initial understanding, the delays happens due to the wire is negligible, and we are not considering at this stage. So even when you look at the DSO, when you generated a square waveform from a function generator, you can see there is a rise time and fall time available for us. That also we are not considering at this stage. These are very key assumptions that we are making in order to design our chip. Okay, because we can easily we will get confused, because if there is a rise time, sir, what happens? Why can't this tool can do? This tool can do, but at this stage we are not going to deal with these topics. And we are also assuming that we have a sufficient space and sufficient modules are available for us to design our idea. And there is no power loss due to race, in the sense that you have for a AND gate, you might have given a supply VDD and VSS. You are connected in the lab. There's a 5 volt here on this one. So in a Verilog code, we are not explicitly saying there is a power rail is there. It is assumed that it is already available in the circuit and it is already mapped for us. And one more thing, from our side, faculty side, we are assuming that you are using a desktop and laptop for online simulation. Okay, that is from our side. Is that clear?
Yes, sir.
So everyone is having a desktop or a laptop in your house?
So I think
No,
there
sir.
are
Some
few
are
who
using
doesn't
phones.
have.
See, in the mobile phone, anyway, we are giving the code, initial code for you. Copy and pasting, that you have to take care. If you want to copy and paste, again in mobile phone it creates issue. If you have a laptop, it is advantage for you. Even if in the mobile phone you can simulate the circuit, we are not saying no for that. You should be aware of how to use copy and paste. At least that level you should know. Is that clear now?
Yes, sir.
Okay. So now we'll go to the main thing. That's how to write a code. I hope everyone knows a C language. Can I compare Verilog code with respect to the C language? Is that okay for you all?
Yes, sir.
Okay, fine. See, in the C language, the first and first thing the compiler sees is a main function. Is that right? It always checks for the main function. The equivalent for the main function here is a module here. Okay, there you can have multiple modules because it is a concurrent way. Okay, and the keyword for that is module. So here we are not going to use a main keyword main, but instead we are going to use a module. Okay. And the once you have created a module, then we have to just connect with the different modules with the wires. How we are connected in the lab. Similarly, we have to just connect through the wires, and we have to see whether all the things are connected. Then we have to execute our code. Only that much we are going to do in a Verilog. So in order to in a module, it has input pin, output pin, and the same pin can act as an in-out. To the extent we will not deal with the in-out pin port, we will be dealing only in the input and output pins. Okay, this is a simple example of how to create a module. Okay, I hope everyone has a notes with you, and if possible, you just note down this scenario how to define a module. So before going for a module, you can see there is a black box available in your right hand side of the screen. So that entire black box is called as a module for us. All your left hand side of your black box is input and the right hand side is output. So in the record or in the observation, you have to follow the same way. Okay, all the control signals normally is given on the top or the bottom. The inputs is to the extent is given to the left hand side of the box, Output is always in the right hand side of the box, and the box which is called as a black box, which will not define what is inside that. So it is called as a black box. So that black box is what the module is going to tell for us. So in this box, we can see there is a module name is available, and I can see in the input pins as well as the output pins. Similarly, I have to define in the Verilog. For that, how I have to write is I have to type a module space the module name, then the open parenthesis, give the ports. Port is nothing but we are going to follow a certain standard, that is first will be output port followed by the input ports. Okay, once you have defined this, make sure you close the parenthesis and that's a semicolon must be there. See, in C language we will not put a semicolon for the main function, whereas here you have to put a semicolon. That is important. This is a common mistake everyone will do. Okay, so to tell that is the end of my module, the keyword is end module. See, there is no space available. End module is a single word, it's not a two word. So I repeat again how to define a module. It is a module space module name, then open parenthesis, first comes the output ports, comma, then followed by the input ports. Once you have completed it, close the parenthesis, semicolon, and once you have written all the logics at the end, we have to go for a end module. Okay, and end module is a single word. How to name the module name? Always start with the alphabet, and you can have a underscore and numbers. So it is recommended you start with alphabet. It is easy for us to understand. Okay, don't start with underscore. Okay, at this stage. These are the examples for the modules. See, for the inverter, we can say module inverter, or I can even name it as a inverter underscore one. Okay, so I have given the, for our entire lab, all the input pins will start with the in underscore. All the output pins will form as a out underscore. Okay, keep that in mind. All our code, what we are going to give, all the input pins will have a in underscore. Similarly, all the output pins will have a out underscore. And always keep in mind, you cannot use a reserved keywords. For example, and is a predefined module available for us, so we cannot use that for our module name. Similarly, for, if, while, switch, which are the common keys in your C language also, we cannot use it here also. Okay, now we'll see how to design a simple inverter. Okay, so as we already told the rules, in order to create an inverter, I have a black box, and the name for that black box is inverter, and I can see the two lines. On the left hand side becomes a input, and the right hand side becomes output port. So we have only one input and we have only one output. As we have discussed here, how we'll be discussing, there is a module space, the module name. Here in the diagram I have used the inverter, so I am using the same name here. And the open parenthesis, the rules is first I have to tell the what is my output. So I have given the name out underscore, the name of the port is Y, comma, in, that's the input side, underscore A, then I have put semicolon, then I immediately type end module. So thereby I am clear that I have defined a box. In this, there is no logic available inside right till now. Okay, just a module is available. That means only the outer layer is available for us. Now it doesn't know what to do with the in and out. The next step is we have to tell to the compiler which is the input and which is output. Okay, see, for our understanding, we have made out Y as output port and in A as a input port, but the compiler does not know whether it is an input or output. So to define it properly, there is a keyword is output, is a keyword which tells that the variable, the name what I'm using after that is a output ports. So output space out Y and semicolon to complete the statement. So it clearly says for me that out Y is a output port. Similarly, for the input, the keyword is input and give space in underscore A. So this gives us, there is a in A which is defined within the inverter parenthesis is for input and out Y is for output. Now I hope everyone is clear how to define an input and output for a module. Okay. Now what we'll do is we will bind the inbuilt function of NOT gate. We are not going to use any symbols here. Instead of that, we are taking advantage of what is already available in the Verilog code. It may be a little bit high level, but it is equivalent to what we say it's a printf statement. If you want to call some functions from the C language, it is similar to that here. So how I have to call the inbuilt module for us? First, we have to give the name of the module. Here it is a NOT. NOT is the name of that module, that for the NOT gate. And U0 is nothing but there is an instance name. For example, I can have multiple NOT gate. So in order to differentiate from which NOT gate I got the output, we are giving a name for that, so that it is easy for us to go for test bench. So we are giving a name as U0. You can give any name. Again, start with the alphabet, then you can have numbers. Follow the same rule. Don't give underscore here at this stage. Then again, open parenthesis. Again, it follows the rule output followed by input. So here, what is my output in the inverter module? What I gave is output underscore y. I am using the same name here, comma, input in underscore a is for my input. So now we have created an inverter for us. So NOT gate is created just by writing a one statement of NOT, U0 and the equivalent ports. Okay, now this is what is converted into equivalent NOT gate. What you are going to study in electronic devices and in the future chapters, that's what it has done now. Okay, now I have created the NOT gate. Now the next job is how do I test a code? So in the digital lab, you have a test bench. That is, you have switches available in your digital lab. So if I want to switch, make it as a logic one, you switch on the switch. Then you'll make sure that your output is LED is glowing or not. A similar kind of approach is done here also. So the rules here is a test bench has three components: input generator, okay, and it should generate its own input, and it should have output, and it should have a device under test. If you don't have a device under test, there is no point in having an input generator and output analyzer. Okay, so what is the job of an input generator? It has to generate what are the inputs required for the device under test. So what is the logic 0 meaning? It is equivalent to the ground. Logic 1 means it is equivalent to the VDD. There is one more thing which I want to introduce, unknown value, but we will use this unknown value in the next lab sessions. So we will not use for this session. Okay, then there's a capture. Capturing is nothing but there's a wire available for which we can connect to the CRO. So this is how a typical test bench will look like, which you have used in the labs also. You have an AND gate in the middle, there's a device under test, you have a function generator, and you have the CROs. And the final point you have to keep in mind, the test bench cannot have input or output ports. Keep in mind, whenever you write a code, the test bench cannot have an input or output. If it has an input and output, then it becomes one more module for us. You are testing again the same test bench module. So okay, how to write a test bench? Again, the rules are same as we have discussed. In a Verilog, again, everything I have to start as a module, and I have module name, and I have open parenthesis, but inside the parenthesis, you will not have any ports, and you just put a semicolon and end module. Similarly, what we have done for the inverter code, we use the same thing. Okay. Now, as we have seen in the previous scenario, we have three blocks. One is input generator, output, and device under test. So in order to generate an input, that means we have to store a value. So we are going to use a key reg for register, which will store the value. So I'm giving reg in underscore a to make sure that I have the same name what defined in my inverter module. My output should be wire. I no need to store any values. Okay, just I have to observe it, then I can discard that value. So I'll be using only wires. Whenever you use a reg, that means it occupies some space in the memory module. So wire means it will not have that much space. So that is advantage for the simulation point of view. Okay. The next is having calling a device under test. Okay, this is same as that of what we have called for the NOT gate. When inside the inverter module, we have called the NOT gate. So it has the same thing. First is a module name. Our module name is inverter here. So our module name is the inverter here. Then followed by the instance name. So I have given a U1 to differentiate with the U0 which I have called for the NOT gate. And how we have written the module here. See, inverter output underscore out underscore y comma in underscore e. That's what we have written here. So I am going to follow the same pattern here. So inverter U1 out underscore y comma. So out underscore y is for my output which I have declared as a wire. Similarly, what is the input? It's a reg. It is in underscore e. So I have given the same thing. So now I have connected this thing. I have declared the required variables and I have connected it, but I have not generated my inputs. So to generate the inputs, I am going to use the keyword called initial. Okay, remember this is the initial is will execute only once for your entire test bench. Okay, anyway, these things will explain in depth in the theory classes. For the lab point of view, just keep in mind initial will execute only once. And this begin and end is equivalent to the flower braces, open braces and closed braces in the C language. Okay. And here I have written the hash file. This hash defines delay in Verilog. So key things you remember, hash defines delay. After the hash, what is the number? So that much delay I'll be having. So hash 5 means 5 time units. Here, each time units by default is 1 nanoseconds. So normally in the Viva, when we ask, this is the way we can confuse you people by saying, instead of saying hash 5, why can't it be 5 seconds? Why can't it be 5 hours? So since each time scale, we are assuming it is 1 nanoseconds, it will be having only 5 nanoseconds delay. And after that, I am assigning into 1. So in this one also, there is a 1 tick B, that means 1 bit, and the data type what I am going to represent is of binary, and the value is 1 or 0. Okay, so first remember, after equal to, I have 1 tick, that's apostrophe, and B, and that means 1 represents 1 bit. Then I have a space. What kind of type I am going to use? We have learned binary, octal, hexagonal, and decimal. So for binary it is B, octal it is O, hexadecimal it is H, and decimal it is D. Then after that, for binary we have only 2 options, that is 0 and 1. That's what we have defined here. Okay. So this is how we can write the test bench. Now I have generated test bench. How I am going to view this? Okay. So since we are going to display only in the screen, we are going to have a 2 function called $display and monitor. Okay. So $display is equivalent to the printf function. Monitor will capture if there's any change in the input or the output values. Okay. We will see how we can write in the code. Okay. And here is a complete code for the inverter and the test bench. Okay, I request everyone to just make a note of it. And the same code is also available in the online. Now you can, if you completed the quiz which comes after this one, you can see the code in the Canvas LMS. Okay, we will just try to run this simulation. Okay. Now. Yeah, I am doing the same way how you people also will do, so that you can see what is the problem in copy and paste. Okay. See, the moment I have copied both the codes, see, first I have copied the inverter module, then I have copied the test bench. Okay. Are you everyone see it properly? Right? So if you just copy and paste and when you give execute, you can see there is a syntax error available for you, right? Okay. So logically there is no error, but the problem is with the font here. Okay, so I'll change this thing. I can see if I change the apostrophe, it changes into red in color. So within the quotes, it changes into red in color. So this has to be there for us. When you copy and paste, normally we'll copy and paste and we just press execute, you'll end up in error. So keep in mind of this thing. And see the keywords also. Automatically it changes the colors. And in the comments, you can see it changes into green in color. Okay. Now when I execute this one, there's one more error. Okay, if I want to see the error, it comes in the line number 18. So line 18, this is the line 18. So again, the tick. Okay. So this, we are unable to change it because of the font available in the system. So when you copy and paste, just change these things. And you can see here. Okay. So now you can see this is inverter test, and this is the name I have given, but the alignment is not proper. That we can change later point of view. Okay. Now I can see at time t is equal to 0, x, both the values is xx, that is unknown value. In digital design, you have learned it is a don't care. So there is a difference here. It is called as unknown in Verilog language. So don't confuse with your digital design letters what you're using and in the Verilog letters. Okay, and after 5 nanoseconds, what we have done here, we have assigned a is equal to 1 for us. So that's what it is done here. After 5 nanoseconds, our value of a is changed to 1, and we can see the output is 0. Similarly, then another 5 nanoseconds, we have changed the input as 0. That we can see here. Another 5 seconds, input is 0 and output is 1. So logically, we have tested the inverted gate. Okay. I just change the format in the monitor so that it is easy for you to understand in the table wise. Okay. So this is a very easiest way to execute. If you don't want to use the Xilinx, Xilinx will take time. This will be executed first. But this does not have a waveform. This can only display a table like this. So in order to display this table, we have to use this predefined function monitor. Remember, this $monitor is a predefined module available for us, predefined function available for us. Okay. Similarly, $display also. Okay, from this point of this lab, I'll just summarize what we have done. Okay. We have seen why we need a circuit simulator. What are the processes involved in the lab? I have given a demonstration of how to do the NOT gate, and we have simulated it. Okay, in the next session, we'll be seeing how to do the AND gate, OR gate, and NAND gate. Again, I will be giving a demo in the next lab. Either me or the other faculties, they'll be giving a demo for you people. If there is any doubt, you can ask now. Hello? Is everyone is clear with the how to define a module?
Yes, sir.
Okay, how to initiate the input and output ports?
So can you tell me the flow, how it goes, how the program get executed? For example, in C, we say main get executed first, but here we have two modules. So what gets
that I will
executed?
explain. Yes, that's a very good question. See, when the compiler sees, okay, there are two modules available. Obviously, we'll get a confusion which is a main module for us. Is that right? Okay. When the compiler sees the two module, when you look at this module inverter, it has a another module called not. Okay. When I go for the one more module, inside this one, I have called the inverter module. Is that right? The inverter underscore TB, I have called the inverter module. So the compiler will make inverter underscore TB as a first module, that's a main one. Then it calls the inverter. So inverter now becomes a sub module of inverter underscore TB. So that compiler will take care of that. So always test bench will be the topmost module, followed by your device under test. Then inside device under test, what are the other modules you have that will be called. I hope I answered your question.
Yes, sir.
Yes, any other thing? Do you have any doubt in writing a test bench? Okay, I believe everyone understood or no one understood.
Sir, I have one more doubt.
Yes.
In that module monitor,
Hmm.
it displays the number whenever there is a change, right?
Yes.
So here time keep on changing. Why it doesn't display 0, 1, 2, 3?
See, when I say time is it will call for the input and output. See, here in the monitor, we have given a in underscore a comma out underscore. These are the thing which it has to monitor. When I use a dollar symbol, it will neglect that. Okay, it is a predefined time series we have. Predefined variable, which the monitor will ignore this type of kinds. Whenever I use a dollar symbol, it tries to ignore that and it takes only the required one.
Thanks, sir.
See, whenever you see the dollar symbol, keep that it is a Verilog function or Verilog variables defined for testing point of view. Okay, only that is only used for testing point of view. Never use dollar monitor or dollar display in your main module here. That is an inverter module. Don't use dollar display or dollar monitor. Okay, because that is not recommended. Okay. Fine. Any other thing?
Yes, sir.
Okay. Then that's it from my side. So now I think the queues will be ready in your canvas. Okay, you can go and attempt the queues. See, this is just a prerequisite queues so that we can understand how we can take this lab easily from your digital design to the next level. Okay, don't worry about your marks, whether this will be considered for the your internal marks or not. This is just for our understanding. So we request you to do honestly so that we can prepare the next sessions in such a way that everyone can understand easily. Yeah, the recorded session also we'll try to upload in the canvas also, so that you can go through it and you can answer also. Okay, is that clear?
Yes, sir.
Okay, then one more thing I forgot to tell, and every week we'll be having a quiz. Depends upon what is the topic we have learned in that week. Okay, just to make sure that we have learned properly. Okay, that's it from my side. Okay. Thank you, everyone. If you have no doubts, you can leave the session. Okay, so make sure you attempt the quiz. It is a limited time is there.
Excuse me, sir.
Yeah, who is this?
Gagan, sir. I had a doubt, sir.
Yes, Gagan.
So, like, ways to write delay function in, like, microcontroller output.
One second. Srisha, and can you mute your mic? Yeah. Yes,
So
Gagan,
we
you can
used
go.
to, like, we used to define a function called delay, like for the repetition, sir. Can't we use
Yeah,
that same thing as a, like,
in
for
Arduino you are
repetition?
speaking.
Yeah, sir.
Yeah.
Like we would to call a function from like other program, like,
Yeah.
so can't we use the test bench or like that?
That's see, for that equivalent only it is given as a hash. See, now that delay function is different. This is a concurrent statement.
Yeah.
Okay, see, I'll present again. That's a very key thing which even I forgot. See, in this one,
Yes.
here I have executed not gate is there, right? So let me type another not gate. I give a name. Let us assume that I am going to give a same variable, same port name. Now what happens here is, in your C language, the U0 will execute first, then U1 will execute second. Is that right? When you normally execute the C language, what happens? The first statement will be executed, that followed by the second U1 statement will be executed. Is that right, Gagan?
Yes, sir.
Okay, now what happens in the Verilog is, both not U0 and U1 will be executed at time t is equal to 0. At the same time, both will be executed. That's why it is called a concurrent.
Yes.
Okay, if I want to delay here, then I have to use a hash function. Hash key symbol I have to use. Okay, then
Okay,
it will delay. But using like this, it will not delay. There's other technique to delay the output side as when compared to the input side. That will teach when you go for the further programs.
No, my question is like, can't instead of writing the inverter modules here, can't we use a function for that?
Not is a module only. Function in the sense you are saying not a function, huh?
It's like for some functions we used to write some like for mat that code, sir. It would execute the other code. So means like for the delay function we used to write other codes, sir. Like for now it's a separate model we need to type now, sir. Like we need to
Okay,
execute it.
I think you
Can't
are
we write it?
instead of writing this big statement, can I write a very small function where it calls it properly? Is that right?
Yeah, like can I define it in other function? Like can I name a file? Can I name a model inverter TB in other tab, and I'm using it in other tabs. So like if I write model inverter TB, will it execute the same function, or like I need to write the entire function?
Okay. I think I got this one. See, here you have module TB, which you can write it in another window, and module inverter, which you are writing in another window. Can I execute will it call the inverter properly? Is that a question?
Yes, sir.
Yeah, it will do. In your Xilinx, we are going to do that only. But in the online simulation, since we have that restrictions, we have to type it in a single window.
Okay.
See, normally what we'll do is first we'll write the inverter code, then we'll create a new file. We'll go for inverter underscore TB. That's a test bench file. Again, we'll write the code. The moment you compile in the Xilinx, it will take the inverter underscore TB as a top module and it will execute.
Okay, sir. Thank you, sir.
Thank you.
ಇದೆಲ್ಲ